Hello and welcome to Non-IITN. So in the previous lecture we had discussed 10 of the problems, and in this particular lecture we are gonna traverse through the rest of the problems, and let's see how many more problems can we typically do. So let's start. Okay, so this is question number 11 from IIT JAM 2024, and what is the question? So which of the following groups has elements of order 1, 2, 3, 4 and 5 but does not have an element of order greater than or equal to 6? Okay. Let us try and understand the things. What are the possibilities for you to have a group of order 6 provided the options? See, if you are concerned about A6, then you can probably work with S6, right? You can probably work with this. And in S6, what are the possible elements of order 6? So you can have cycle decomposition 6, you can have cycle decomposition 2, 3 and 1. So you can have 1, 2, 3. And what are the other possibilities to get hold of an element of order 6? And what you can do is that you can't add more 2's, right? So these are the only two possibilities as far as I can observe, right? So will this actually give you an element of order 6? I don't think, right? Because this has an so this will provide with, so it's a 3 cycle, right? So 3 cycle means 4 transpositions with another transposition, so it gives you 5 transpositions. And you have 6, that is a 6 cycle, so it gives you 7 transpositions. So both of these contribute to even cycles, odd permutations. So none of these elements are of order 6, so therefore A6 will not have an element of order 6. But will it have elements of the other possible orders? See, element of order 1 is quite easy. Element of order 2, you can take probably 2 cycles, right? You can work with 2 cycles, let's say 3 and 4. So the LCM of their orders will be the LCM of 2 and 2, which will give you 2, right? Because this comes with the element, let's say 2, 2, and you can take the rest to be 1 and 1, right? So it will have order 2 and it's an even permutation. So 1 is there, 2 is there. What about 3? So a 3 cycle is an even permutation, right? So 1, 2 and 3. So this will come out to be an even permutation. So 3 also works. What about 4? So a 4 cycle, 1, 2, 3 and 4, it's an odd permutation. But if you add 5 and 6, this will give you an even number of permutations. So an even number of transpositions. So it will become an even permutation. So it's in A6. And what should be its order? So its cycle decomposition is 4, 2. So its order is LCM of 4 and 2, which is 4. So it's of order 4. What about 5? So yeah, you can take a 5 cycle, right? So you can take a 1, 2. So you can take 1, 2, 3, 4, 5. So it's a 5 cycle. It's an odd cycle, so it's an even permutation. So A6 will work. So this was an observation kind of a problem, and you can actually check that in B, C and D you will either not get an element of all possible orders as provided, or you will get an element of order 6. For example, in S6 you will obviously get an element of order 6, right, which is the 6th cycle. In S5 you will also get an element of order 6, which is the cycle, let's say 1, 2 and 3, 4, 5. A 2 cycle and a 3 cycle will give the LCM to be 6. So you will get a 6 cycle, get an element of order 6 here and element of order 6 here as well. Check for alternating group of 5. I hope it won't be an issue. Okay, let us move on to the next question. Okay, so this is the interesting question. What does it say? Consider the group G to be the collection of all elements in matrices in 2 cross 2 real matrices, such that A times A transpose is identity. Okay, so these are orthogonal matrices. So G is the what we typically refer as O2. So these are orthogonal matrices. And orthogonal matrices have a very important topological property that these have 2 connected components. Fine, nevertheless, that is not our concern at this point. So we are given this with respect to matrix multiplication, and we are given the center of it. So we are being asked that what is the cardinality of the center. Okay, so See, typically the collection of all orthogonal matrices, these are typically reflections and rotations. Okay, so rotations, they contribute to the matrices having determinant 1, and they contribute to the matrices having determinant -1. Okay, so these are the only two types of matrices which constitute these orthogonal group. Okay, now what about the elements which commute with both these groups? Now let me tell you a very a subtle point here. This point exactly won't be that rigorous in nature, but let me tell you. So this is, you can take this to be a phrase which is highly relevant to matrix groups. That is, if A is a, or let me use, suppose lambda is a collection of a large set of matrices, possibly a large set of matrices, then the center of this is, approximately always collection of scalar matrices. Okay, so if you have a considerably large collection of matrices, because there are obviously large number of possible orthogonal matrices. In case of orthogonal matrices, what do you need to do? So for orthogonal, to construct an orthogonal matrix, you just need to take the columns to be mutually orthogonal. That will typically help you out. Okay, nevertheless, that is not something which we are too much concerned about, but the main fact is that if you have some collection of matrices which is considerably very large, then the center of that particular collection more or less comes out to be the collection of scalar matrices. So if you assume this phrase to be true in some sense, you will obviously get the result. That is, if you take any matrix of the form lambda I, then first of all, these elements must be in G, so their determinant should be 1. The determinant square should be 1, because this times its transpose should give you identity. But that would mean lambda square is equal to 1, which means that lambda is equal to plus or minus 1. So in that particular case, you get only two elements, I or minus I. So the center will have two elements. But what probably can be, a more rigorous approach to this particular problem? See, something which you can think of is that suppose R theta is the matrix which considers the rotation by theta, then all rotations commute with each other. Okay, so R thetas commute with each other. Okay, they more or less commute with each other. Now if S is a reflection, then you probably, if you recall how do we typically have the dihedral group, then we will be able to verify that if you apply a if you first apply an inverse reflection, that is reflection opposite to what S is conventionally designed to be, then you apply a rotation by theta and you reapply the reflection, you will get the reverse rotation. Okay, so the verification of this is standard dihedral structure. Okay, this is standard dihedral structure. So for R theta to commute with S, what do you need to have? So therefore, if R theta commutes with S, because that is all what we need, then what should you have? You should have R theta is equal to R minus theta. So therefore, rotation by an angle theta counterclockwise should be same as rotation by an angle theta clockwise. But what is the only possibility here? So this implies that theta is an integer multiple of 2 pi, right? Is an integer multiple of 2 pi, because see, after all, this theta, this rotation can be actually considered like e to the power 2 pi I theta. That is what actually gives you the rotation typically, right? If you assume this to be from the complex field, and we know that this is 2 pi periodic, and geometrically it's also very easy to observe that if you start from some particular axis and you take a rotation from any side, counterclockwise or clockwise, by an integer multiple of theta, you will come back to the same axis, right? So but what does that mean? So this means that so if 2 theta is a multiple of 2 pi, so what does that mean? So theta must either be 0 or theta must be equal to pi, right? if I restrict myself within 2 pi's, so what does that mean? So hence r theta is either identity or minus identity, right? Clear? But obviously reflections do not commute with all rotations. That's quite obvious, right? Rotations will commute on this particular scenario, but reflections obviously do not compute with all rotations at any cost. So therefore the only elements you will be able to catch hold of as elements in the center are these, and hence there are only 2 elements. Let us move on to the next question. So which of the following statements are true? The additive group of, okay, so this is probably a misprint. There is no complete question, so we'll verify this later. Let us move on to the next question. So okay, so this is a question from TIFR GS 2024. Let us see this particular problem. So we are given that 2 statements. Okay, so G is a group and H is an element in G. Sorry, it's a subgroup of index 2. Then the commutator of G is contained in H. Okay, and if G be a group and H is contained in G that contains the commutator, then H is a normal subgroup of G. Fine. So if you know about the commutator, then this is actually a very easy problem to concern about. So solution. What is typically the commutator? So the commutator is the subgroup generated by all elements xy in G, where this is called the commutator of x and y, and this is basically the elements of the form xy x inverse y inverse. So I can just write it as xy x inverse y inverse. Clear? See, now basically what you can probably see from here is that suppose if H is a subgroup of G such that the index of H in G is 2. So this implies that firstly H is a normal subgroup of G, and so you can see that, go back to the theory lectures to get hold of this particular statement. We have discussed this in previously, that if you have a subgroup of index 2, then that particular subgroup will come out to be normal subgroup. But something more which we can conclude here is that I mean not here, in every such scenario, is that G mod H is isomorphic to Z2, and this implies that G mod H is cyclic, right? In fact abelian, and hence abelian. Now this is a very important result which you can probably try and prove. It won't be that difficult, I hope. That is, if G mod n, a particular quotient group is abelian, then the commutator subgroup is contained in N. Typically the commutator subgroup is defined to be the smallest possible subgroup such that the quotient is abelian. Okay, so what does this mean? So from here we can conclude that the commutator subgroup will obviously be in H. So the first statement is obviously true. What about the second statement? So it's saying that the commutator is contained in H. What can we say about the normality of H? Okay, so let me just phrase it first, which I just said. That is, this is the smallest normal subgroup of G such that G mod a quotient is abelian. So if I take this to be H, is abelian. Okay, now if H is any subgroup of G containing this, okay, then by the correspondence theorem, what should you have? That H is normal in G. That should be the answer, right? Because normality is preserved in the correspondence. So did I talk about the correspondence theorem during the theory lectures? I don't think so, right? Okay, so let us discuss a bit of the correspondence theorem. Let me just go for a new page at this point. Let me take just this page. Yeah, so we are going to talk about the correspondence theorem. So the correspondence theorem, probably I've just forgot to tell about this, but the thing is actually very 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 easy, not that difficult. So basically the correspondence theorem says that let so let G be a group and let's say N be a normal subgroup of G, then there exists a 1-1 correspondence. There exists a 1-1 correspondence between subgroups of G containing N and subgroups of G mod N. Okay, so let us define this formally. So let G be a group and let's say N is a normal subgroup of G. So let us define S to be the collection of elements which are subgroups of G such that N is contained in H, and let tau to be the collection of subgroups of G mod N. Then we have a precise map. So we have a map from S to tau by phi taking H to H mod N, and this phi is actually a bijection with phi inverse, which we can take to be, for example, psi to be a map from tau to S, given by, so psi of k is just the fiber of k, so it's the projection fiber of k, where pi from G to G mod N is the natural projection. Okay, and the more important properties of this particular theorem is that this correspondence is inclusion preserving, is inclusion, normality, and finite generation preserving. Okay, is preserving. Clear? So once you have this particular theorem in hand, you already get hold of a proof of this particular statement. So now I can firmly say that, so this follows from the correspondence theorem. Let us move on to the next problem. So if G is a group of order 361, then G has a normal subgroup H which is isomorphic to G mod H. So let us see a solution of this. Now I probably think this is not true, because when you have solved a lot of problem, you'll have an intuition that some statements seem to be not true. Let's see. So G has order 361, and 361 is, you should know, it's 19 squared, right? So it's a group of order p squared, so it's abelian, so therefore it's an abelian group. Therefore G is either isomorphic to Z19 squared or it's isomorphic to Z19 cross Z19. So let us work with one of these examples. Suppose I work with the cyclic group. So let G be exactly equal to Z361, and it's also a P group. So I can choose. So let H be, for example, the group Z19. So it can be identified as a subgroup of G, because a group of order 19, it is having a prime order, so it's automatically cyclic, and every group of order p to the power n constitutes all the subgroups of order p, p squared, p cubed till p to the power n, and all of these are normal. Moreover, it's an abelian group, so every subgroup will be normal. But then observe that H cross, now what is G mod H? So it should also be isomorphic to Z19. So by the statement you have Z19 is okay. So I think this works, right? Yeah, so it's working. Okay. So it is working for Z19 squared. Fine. Okay. Acha. What about Z19 cross Z19 now? Okay, I think it will be true. It will be true. Okay, this is a true statement. I do not need to even consider all these things. I can do this in the following sense. Now, this holds true for all groups G of order p squared, in fact, because if you have a group of order p squared, then you will have a group whose order is p. In that case, G mod H will also have order p. Both of these are all groups of order p, so they are isomorphic to Zp, right? So it works, so it's true, right? So I claimed it to be false and I eventually came out to the fact that it's true. And this is what typically happens in the true or false type of statements. You need to work through some particular assumption and you will either contradict your own assumption or you'll get hold of a proof through contradiction. Very, very ironical. Let us see the next problem. So let G be a proper subgroup of R plus which is closed as a subset of R. Then G is generated by a single element. So this is a very fine problem and the problem resides in only one particular statement. So solution, the statement is the following: every subgroup of R plus is either dense or cyclic. And this is a very important theorem in the theory of topological groups. So if you have a proper subgroup which is closed, so it cannot be dense, so the only possibility is cyclic, so it's generated by a single element, so it's true. Okay, that was a good question. Let us move on to the next question. With the number of finite groups up to isomorphism with exactly 2 conjugacy classes. Okay, so let's see this particular problem. So let G be a group, a finite group, such that G has only 2 conjugacy classes. And let us name them, say C1 and C2. Now, obviously, let C1 be the conjugacy class of, let's say, identity. Okay. Then what do I have? Then obviously the order of C1 would be just 1. Also, we know that conjugacy classes come out as a result of an equivalence relation. So these are basically equivalence classes. Also, the cardinality of G is exactly the cardinality of C1 plus the cardinality of C2. So this is equal to 1 plus the cardinality of C2. Okay, fine. Okay. What more can we say? Okay, also recall the cardinality of a conjugacy class is given by the cardinality of G in case of finite groups divided by the so conjugacy class of some element A, it's given by the centralizer of A. What does that mean? That the conjugacy class, it actually divides the order of G. So therefore, so if the conjugacy class of 2 divides the conjugacy class of G, what does that mean? That means the conjugacy class of 2, which is exactly equal to conjugacy class of G minus 1, this divides the conjugacy class of G. I mean, say cardinality of G, I'm extremely sorry. But the only possibility in this case will be the cardinality of G is 2. Right? 2 is the only element which is divisible by an element which is exactly less than 1. but there is only one group up to isomorphism of order 2, so therefore G has to be isomorphic to Z2. So there is only one possibility. Okay, let us move on to the next question. The number of elements of finite order in the group. Okay, fine. This group is very well known, I guess. So I think it's something which I know. Okay, so this is the Heisenberg group, I guess. Yeah. So this is the Heisenberg group. Yeah, this is a famous name. It's called the Heisenberg group over R. Okay. Now the important fact here is the following. That is, if you choose any element, so let me write the solution. So the group provided is called the Heisenberg group over R of dimension 2 cross here you have 3 cross 3. Okay. Now what do you typically have here? Now observe that if A belongs to this group, so let me denote this by H, or let me denote this by a stylized version of H. So suppose I take this to be H. Then observe that A can be written as identity plus a matrix which is nilpotent. A matrix which is nilpotent. Right? Because you can just separate out the ones and the matrix with all the elements being the upper dominating triangular matrix with the elements A, B, C in the upper triangular portion. But what can you typically conclude from there? So what do I have here as N? So this is nothing but 0, 0, 0, A, B, C, and here you have 0, 0, 0. But what do I have here? So this would obviously mean that N cubed is equal to 0. Now if A has finite order, say A to the power k is equal to identity, then A to the power k is nothing but I plus n whole to the power k, which will come out to be I plus k times n plus k into k minus 1 upon n, because we have identity, so it will obviously commute, upon 2 times n squared, and the other will become 0, right? All the rest of the elements will become 0 because n cube is equal to 0. So this is equal to identity. But what does this imply? So this implies that n squared is equal to no, am I doing it correct? So I will get cancelled out. Yeah, so this implies that n plus k minus 1 over 2 times n squared is equal to 0. We'll get this right, because you can just cancel out by k. K will obviously be a positive integer. What then? So this implies n squared. So if I multiply by n on both sides, you'll get by 2 times n cubed will become 0. But then since n cubed is 0, so this would imply that n squared is equal to 0. But once n squared is equal to 0, that would imply n is equal to 0. Once n is equal to 0, that would imply A is equal to identity. Okay, so you will get only one element. So only one element having finite order. That was a good proof. Let us see the next question. Suppose G and H are two countably infinite abelian groups, okay, such that every non-trivial element of G cross H has order 7. Fine. Then G is isomorphic to 7. Now see, typically, at least I feel that this should be true, because the first example which is coming to my mind is okay, so they are wanting you to have two countably infinite abelian groups. Okay, So first of all, this comes out to be every element of G cross is order 7, then G cross H will obviously be a P group, an infinite P group it will typically be. Okay. Okay, let's see a proof of this. Let's try to consider a proof of this. See, the first thing which I can argue from here is that since G cross H has every element of order 7, then the characteristic of G cross H has to be 7, right? But what does that mean? That means I can consider G cross S as a vector space over F7, right? Because you know that if you have an abelian group of characteristic P, then you can consider that to be a vector space over Fp. So an abelian group of characteristic P is a vector space over Fp by the very natural operations. Okay. Now what do I have? Now what should I do from here? Now we know that if dimension, so this is another statement. I should try and continue this. Now if V is a Fp vector space of dimension n, then the cardinality of V will come out to be P to the power n, because we will have a basis, an Fp basis of V. Okay, so that basis will constitute of n elements. So if you take any element as a linear combination of those, you will get P choices for each of the elements, right? Because you will be taking the coefficients from Fp, so you will have P to the power n total number of possibilities. Okay, so therefore if G cross H is finite dimensional over Fp, then G cross H has to be will this work? Do I need to consider them to be finite dimensional? I don't think so. Do I need them to be finite dimensional? See, something which we can see from here itself is the following thing, that G cross H forms an Fp vector space, right? See, now G cross H forms an Fp vector space. What does that mean? That means that G and H have component wise operations as an Fp vector space. Clear? So this would mean that G and H are also, so we have F7 vector space here, are also F7 vector spaces. But yeah, so now I think we can have this action. Now G and H cannot have finite dimension, because then it will be finite. Cannot have finite dimension, then they will be finite. So both are both will be LF naught dimensional, because they are countably infinite. So both are LF naught dimensional vector spaces over Fp, and two vector spaces of the same dimension are isomorphic as vector spaces, and hence over the same field obviously, and hence isomorphic as groups. And two vector spaces over the same field having same dimension are isomorphic. as vector spaces, but then you're going to translate them to group because they are after all groups. They are underlying, they're having an underlying abelian group structure. So this will be also be true. Okay, so this was again a very good proof. Let us move on to the next particular problem. So it's already a 35 minutes long lecture. We will take to problem question number 20 and question number 21. Let's see. So there exists a non-abelian group G of order 26 such that every proper subgroup of G is probably this will be abelian. True or false? So let's see the solution. So first, when I see what is the order of G, it's 26. So it's 2 times 13. So it's of the form 2p. Now a group of order 2p, it's either isomorphic to Z2p or it's isomorphic to dp. These are classical result in finite groups, that if you have a group of order 2p where p is an odd prime, then it's either isomorphic to Z2p, that is a cyclic group of order 2p, or it's isomorphic to the dihedral group acting on a regular polygon of with p sides, p vertices. So we are concerned about non-abelian groups, so this obviously won't be the case. So we need to work with dp. So we need to work with, so dp is the group we are concerned about. But what are the only possible subgroups of dp in this case? You will have a subgroup of order 1, you will have a subgroup of order 2, but those will be automatically cyclic, and you will be possibly getting a subgroup of order 13 because those are the only possible divisors of 26. There are no other possibilities, right? So each of those will be typically abelian, right? Therefore this is true. So there exists a non-abelian group G of order 26 so that every proper subgroup is abelian, because every proper subgroup will be automatically abelian given the possibilities of the suborder of the subgroups, right? So only thing which we had to be concerned about this particular problem is that whether there exists a non-abelian group or not, which surely exists. Okay, what is question number 21? Let P be a prime number. What is the number of elements in the group Q mod Z that have order exactly P? So basically, if you have Q mod Z, then an element of order n is exactly, number of elements of order n is exactly phi n. Okay, so in Q mod Z, number of elements of order n is exactly equal to phi n. So therefore, if n is equal to p, then phi of p is equal to p minus 1. So p minus 1 should be our answer. Okay, let us see question 22. There are only finitely many isomorphism classes of finite non-abelian groups, all of whose proper subgroups are abelian. Okay, so let us stop here itself. We will talk about problems from 22 to 34 in the next lecture, but I'm just giving you a hint. Probably this particular thing is false, and as far as I think, I'm not sure, quite sure about this particular problem, but I think there is something to do with groups of order PQ where P divides Q minus 1, that is Q is congruent to 1 mod P. Okay, I've got the proof. We'll come to this in the next lecture, but I've got the proof. So there is a famous theorem of Dirichlet, that is, there are infinitely, so given a prime P, there are infinitely many primes Q such that Q is congruent to 1 mod P. So you will get infinitely many groups of the form PQ where P divides Q minus 1, and we know that there is a possibility for these groups to be non-abelian, and even if these groups are non-abelian, the only possibilities of the subgroups are of order P or Q, the trivial or the whole group. The whole group is non-abelian, but we are given proper subgroups, so the proper subgroups are having only order P or Q or trivial group, all of which are abelian. So this is false, right? There are infinitely many. So this comes with the Dirichlet theorem. Okay, so we'll meet in the next lecture where I'll try and give you a hint to how to prove this Dirichlet theorem. Actually, I have a proof of this using Galois theory, not exactly Galois theory, but specifically field theory. But I'll see that whether that will be an easier approach, or rather we should go through a number theoretic approach. We'll see that in the next lecture. Okay, so meet you guys in the next lecture.